Welcome back to the MbaguMedia Tech Talk podcast. Today, we're diving deep into a topic that's critical for every organization: cybersecurity vulnerability prioritization. For years, we've relied on systems like CVSS, but the landscape is changing, and we need smarter solutions.
That's absolutely right. The Common Vulnerability Scoring System, or CVSS, has been our go-to, providing a numerical score for severity. But as we'll discuss, it often falls short of capturing the real-world, dynamic nature of how vulnerabilities are actually exploited.
Exactly. Think of CVSS as a basic grading system that might tell you an essay is long enough, but it doesn't tell you if the content is compelling or impactful. Vulnerability descriptions, on the other hand, are rich with narrative. They tell us how an attacker might get in, what skills they need, and the potential damage.
And these descriptions contain vital clues about the attack vector and complexity. Is it a simple click, or does it require intricate social engineering? These granular details are precisely what a simple numerical score struggles to quantify, yet they are crucial indicators of true danger.
This brings us to our core idea: we can create a much more adaptive and accurate prioritization system by leveraging machine learning, specifically through semantic embeddings and smart feature engineering. We're aiming for a paradigm shift, moving from reactive triage to proactive, intelligent risk assessment.
It's not just about a better score, it's about fundamentally transforming how we perceive and manage cyber risk. Natural language processing, or NLP, is pivotal here. We're transcending simple keyword matching to achieve a deeper, semantic understanding of vulnerabilities.
So, let's start with the foundation. Section 1, the data foundation: ingesting and structuring vulnerability intelligence. Building this system requires a solid base of high-quality, well-structured data. The National Vulnerability Database, or NVD, is our primary source, but it has its limitations and variability.
Absolutely. This is why a robust data ingestion pipeline is so critical. We need to fetch CVEs, but also manage constraints like API rate limits gracefully. Data integrity throughout this process is non-negotiable. Our assessments are only as reliable as the data they're built upon.
And what happens when the NVD API is down or errors occur? This is where graceful degradation and fallback mechanisms become essential. We need the capability to generate synthetic data, not fabricated vulnerabilities, but realistic points that mimic real CVEs to ensure system continuity.
That's a smart approach. Once the data is secured, whether from the API or synthetic generation, we transform raw CVE records into a structured dataset. This involves extracting essential metadata like publication dates, existing CVSS scores, and known attack vectors.
But the real gold is in the vulnerability descriptions themselves. They are the primary wellspring of semantic information. We also meticulously identify and extract structural features that influence risk, like the number of references or specific CVSS v3 components.
And all this data needs normalization. Different CVE versions and reporting styles can cause inconsistencies, so we ensure uniform formatting for downstream machine learning processing. This clean, enriched dataset is absolutely crucial for our models to learn meaningful patterns.
Moving on to Section 2, bridging text and data, semantic embeddings and feature engineering. This is where ML and NLP truly shine. Simple keyword matching is a blunt instrument, it misses context and nuance.
Exactly. Semantic embeddings are key here. Think of them as translating human language into a mathematical language computers understand. We use transformer models, like all-mini-LM L6v2, to convert text descriptions into dense numerical vectors that capture underlying meaning.
The power of models like all-mini-LM L6v2 is their efficiency and ability to grasp nuanced linguistic relationships, especially in specialized cybersecurity jargon. But embeddings are just one piece of the puzzle. We need explicit feature engineering too.
This involves defining and extracting critical keywords and patterns. We create categories like execution, injection, authentication bypass, and flag the presence of high-risk characteristics. Simple textual statistics, like description length, also offer valuable information.
We also manage categorical data like attack_vector and privileges_required using techniques like one-hot encoding to transform them into numerical formats. The real innovation comes from this hybrid approach, fusing semantic embeddings with structured features.
This fusion allows the model to learn from both explicit data and the implicit, contextual meaning within the text embeddings. This meticulously engineered feature set acts as the crucial bridge, transforming vulnerability descriptions into actionable intelligence.
Now, let's talk about Section 3, the Learning Engine, Building and Training Predictive Models. Our goal is to develop a dynamic, ML-driven priority score that reflects real-world risk, moving beyond static CVSS limitations.
For predicting severity classes like low, medium, high, and critical, we're using a random forest classifier. These models are robust, handle complex relationships well, and are less prone to overfitting.
And for predicting a continuous score, similar to a refined CVSS, we're using a gradient boosting regressor. This technique excels at capturing nonlinear patterns and intricate interactions within the data.
The magic happens when we feed these models a combined feature space, our structured features integrated with the semantic embeddings. This creates a single, rich input matrix for training. It's like giving the model all the essential puzzle pieces.
Before training, data scaling is crucial. Features can have vastly different magnitudes, and without scaling, models can be biased. Standardizing ensures all inputs are treated equitably, allowing models to learn more effectively.
Then comes training and validation. We partition data into training and testing sets. The training set educates the models, and the testing set evaluates their performance using metrics like classification reports and root mean squared error, RMSE.
The result is a sophisticated model capable of predicting a dynamic, ML-driven priority score, often a composite of predicted severity and nuanced risk. We can also conduct feature importance analysis to understand why the model makes certain recommendations.
This moves us toward explainable AI in cybersecurity, building trust and understanding. This meticulously trained engine can dynamically assess and rank vulnerabilities based on learned patterns, offering a far more sophisticated risk assessment.
Let's shift gears to Section 4, Uncovering Latent Threats, Clustering and Pattern Recognition. Beyond individual scoring, there's immense value in identifying systemic risks and recurring exploit themes. This is where clustering, powered by our semantic embeddings, comes in.
Instead of just looking at each vulnerability in isolation, we can group them based on semantic similarity using algorithms like k-means clustering. Visualizing these embeddings often reveals distinct groups representing vulnerabilities with common linguistic DNA.
And each cluster can be analyzed to understand its characteristics, average CVSS, traditional severities, and dominant keywords. For instance, a cluster might be dominated by buffer overflow and memory corruption terms, indicating a specific type of recurring vulnerability.
The insight here is profound. These clusters can reveal common attack vectors, specific types of vulnerable software, or exploit techniques that might be missed when focused solely on individual CVEs. It's about uncovering latent relationships and potential attack chains.
Understanding which clusters represent the most immediate or widespread threats allows for more strategic defense planning. The beauty of analyzing cluster keywords is its ability to provide human-readable interpretations of complex semantic relationships.
This capability extends to identifying emerging trends. By continuously analyzing new vulnerabilities and observing how they fit into existing clusters or form new ones, we can detect shifts in attacker methodologies or the rise of new exploit classes.
This proactive identification allows organizations to bolster defenses against anticipated threats before they become widespread. The ability to group vulnerabilities by semantic similarity offers a unique lens to view the threat landscape, highlighting interconnectedness.
Finally, we reach Section 5, Actionable Intelligence, Visualization and Decision Support. This is where we translate complex ML outputs into digestible intelligence for security teams. Visualization is paramount here.
Charts and dashboards transform complex data into understandable insights. We visualize the distribution of our ML-driven priority scores, identifying tiers of true risk and the vulnerabilities demanding immediate attention.
Comparing our ML priority against traditional CVSS scores clearly demonstrates where our new system diverges and why. This comparison fosters trust and understanding in the ML model's recommendations. Visualizing feature importance is also key for transparency.
Representing vulnerability clusters visually provides a clear overview of identified groups and their prevalence, aiding in spotting thematic threats. Visualizing attack vector distributions offers a concise snapshot of significant exploitation modes identified by the model.
Ultimately, all this culminates in presenting the top priority vulnerabilities in a clear, ranked list. This includes the CVE ID, our ML score, the original CVSS score, and a concise snippet of the vulnerability description.
The goal is to empower security teams to make faster, more informed decisions. We guide them away from brute force CVSS triage towards intelligent, context-aware risk management. Summarizing actionable takeaways provides a clear roadmap for response.
This integrated approach effectively transforms raw analytical output into strategic decision support, closing the loop from data to effective defense. It ensures that insights from sophisticated ML models are understood and acted upon.
And that brings us to the conclusion: towards adaptive and intelligent vulnerability management. We've explored how to move beyond the limitations of static CVSS scoring to embrace an intelligent, adaptive prioritization system powered by ML and semantic analysis.
By integrating natural language embeddings, structured metadata, and ML models, we've built a system that more accurately mirrors the dynamic reality of exploit risk and operational urgency. This lays a robust foundation for truly adaptive security pipelines.
It represents a commitment to building intelligence directly into our defenses, transforming how we identify, assess, and respond to cyber threats. We're shifting from a reactive posture to a proactive stance, informed by a deep, contextual understanding of risk.
The implications are substantial. Security teams can allocate resources more effectively, focusing on genuine, immediate threats rather than being overwhelmed by misleading static scores. This leads to more strategic patching and a more resilient security posture.
This journey from raw data to actionable intelligence is complex, but by embracing these advanced techniques, we can navigate the cybersecurity landscape with greater foresight and efficacy. This is the future of vulnerability management: dynamic, intelligent, and adaptive.
Now, let's quickly recap the key takeaways from our discussion, breaking down the summary table. First, under key factors, we have data ingestion and structuring.
Right. The strength here is a robust pipeline that accesses critical data like CVEs, manages API limits, and uses synthetic data as a fallback. The challenge is the variability in data presentation from sources like NVD, requiring ongoing effort for consistent quality.
Next, semantic embeddings and NLP. The strength is using transformer models to grasp nuanced meaning beyond keywords, capturing relationships and intent. The challenge is the computational cost, but the opportunity lies in exploring advanced NLP techniques for better accuracy.
Then we have feature engineering. Combining structured data with semantic understanding creates a powerful hybrid feature set. The challenge is identifying the most predictive features, but the opportunity is to discover new impactful features and automate the process.
Following that is machine learning models. Utilizing models like random forests and gradient boosting allows for accurate prediction of severity and risk scores, learning complex patterns. The challenge is model interpretability, but the opportunity lies in developing more explainable AI techniques.
And finally, clustering and visualization. Clustering semantic embeddings reveals hidden relationships and systemic risks, while visualization translates data into actionable insights. The challenge is interpreting clusters, but the opportunity is in developing interactive, automated visualization tools.
So, to summarize the strengths and insights, we've seen how a robust data foundation, advanced NLP for semantic understanding, intelligent feature engineering, powerful ML models, and clear visualization all contribute to uncovering latent threats and providing actionable intelligence.
And looking at the challenges and opportunities, we must address data variability, computational costs of NLP, the need for domain expertise in feature engineering, model interpretability, and the complexity of translating cluster insights into action. The opportunities lie in automation, advanced techniques, explainable AI, and dynamic visualization tools.
This comprehensive approach truly moves us beyond the score to a more intelligent, adaptive, and effective way of managing cybersecurity vulnerabilities. It's an exciting evolution in the field.
Absolutely. Thank you for joining us on this deep dive into revolutionizing vulnerability prioritization with AI. We've covered the introduction, all 5 sections, the conclusion, and the complete summary. Join us next time on MbaguMedia Tech Talk.
Thanks for listening.